because it's a thermodynamic process of phase inversion, and from a polymer, lean phase to a polymer rich phase, mixing it in the anti-solvent, all those diagrams we talked about. So today I'm going to talk about what are the different, configurations of the membrane, particularly what types or shape or geometry of these membranes could be, what are the possible module arrangements. So please recall or please note that these membranes do not act as a standalone unit, and they are actually fixed in a module, right? And it is the module design that plays a big role in the flow configuration, to some extent on the performance of the system also. So both the membrane characteristics, its properties, its shape configuration is important, as well as the module. By module, we will soon realize what do we mean by the module and what could be the different possible configuration or types of the modules. The modules also play a big role in in the assessing or in determining the performance of the system. Now, when I talk about these membrane configurations, typically membranes could be of a flat sheet. A flat sheet membrane is typically like a piece of paper, where that sheet itself is porous. So you can think of these sheets to be nothing but your filter paper. All of you must have seen this filter paper in your high schools. So these are essentially sort of sheet membranes you can think of. The other most popular type of the membrane configuration is the hollow fiber. So how does a hollow fiber look like? So it's a kind of hollow, core through which one liquid flows, and particularly the liquid which the containing the contaminant, and the cylindrical surface area, right? The cylindrical surface area. So this surface area, the cylindrical surface area is actually porous, and this is what the membrane is. So the fluid which is flowing in the core of this hollow, channel will be at a higher pressure, or will be at a higher, chemical potential compared to the fluid or the system outside of this hollow fiber. So because of the difference in this chemical potential, there will be transport, right, through this porous layer. Now this porous layer could be very selective to the particular kind of solute we are dealing with. It, the properties of this porous wall, which is essentially the membrane here, determines that what would be the rate of transport, what would be the separation efficiency, all those parameters, right? So this is one other configuration where you have this hollow fibers. So it's like a blood capillary, how you have diffusion across the blood capillary, very similar to that. These are polymeric structures with having porous wall, and in the core you pass the contaminant liquid, and through that, on the cylindrical surface area, radially outward, the filtration happens. So this is what we mean by the hollow fibers. I will immediately talk about how these membranes are prepared. But before that, just to give you a glimpse of the different types. So these are generally the different types. There is also another type known as the tubular, membrane. This is not very common, but this type also do exist. A tubular membrane, or sometimes these are also called monolith, is essentially a big, kind of this hollow fiber arrangement, but you have multiple channels in that core. So it is like you can think of a big tube like this, and where you have small holes, multiple holes in one of the big, tubes. Right. So this entire block or this big tube or dimension is sort of, a porous material, and these are the hollow cores into which the liquid or the fluid will pass. And through the circumferential, through the cylindrical surface area, the filtration will happen, because through these small cores, you will have the flow or whatever the fluid is passing is at a higher pressure, right? And through this cylindrical surface area, you will essentially be having this filtration. So it's like a multi-channel kind of hollow fibers. But even though the thickness of the what should I say, the porous region is not uniform radially, right? In the hollow fibers, it is like the thickness is uniform, right? But here it is not the case. So if I try to see a top view of this tubular membrane, it looks something like this. So these are the porous region. Right. So these are, and through this you have the hollow channels through which the liquid will pass or the fluid will pass, and the entire shaded region is porous in nature, right? Through which the filtration will happen radially. Now these sort of structures or the tubular membranes are generally prepared of ceramic membranes, because they needs to be particularly strong to handle multiple channel flows. Hollow fibers could be of ceramics, could be of polymers. Flat sheets are generally of polymeric materials. So this is what we talk about the membrane configuration. Let us quickly look into how do you prepare these membranes. So typically, I will talk about mostly the polymeric preparation because that's easier to prepare. Ceramics ones are slightly more complicated in nature. So polymeric ones, as you know, the basic principle is the phase inversion. So you have a polymer solvent system, and that is like, then placed. I mean, it's a very viscous solution, and that is now when it is placed in the, what do you call, in the anti-solvent, which is water, it will move from polymeric rich phase to polymer lean phase, right? And that's how the phase inversion will take place, right? So here it is like the fabrication of the flat sheet membranes, and the arrangement is very similar to how do you prepare your paper rolls. So here first you have a polymeric solution, and since the polymer concentration is very high, this sort of semi-solid kind of viscous solution can be created like a film and passed on to the rollers, right? It will create like a film, and you can actually pull that film. It is so viscous, right? And that flame, once it get introduced into the water bath, it will start to have the gelation effect, and it will become solidified. Once it becomes solidified, it will become more like a sheet, and now that is pulled through several layers or several such rolls, so that the residence time in the water is more, and proper demixing of the solvent and the water takes place. The pores also becomes fully matured in the polymer, and the polymers sheets are also get to some extent stretched, so that their properties etc. are more uniform. And after adequate residence time, they are then put into the drying chamber. So this is how a sheet or a roll is of the membranes are prepared. How do you prepare a hollow fiber membrane? The arrangement is slightly tricky here, because you have to create a hollow core. So what is the technique or the idea? You generally have this sort of coaxial needle arrangement. Just try to focus this region. From if you look into here, there is an inside needle through which generally you pass water, and the outer peripheral region surrounding this internal region you pass the polymeric solution, right? So the internal hollow, this whatever this water channel or this water line is there, that will try to have this phase inversion on the interior or the inside surface of this membrane. So there will be a coaxial flow, right, of the polymeric liquid, and in the inside you will have this water flowing. So the inside will be solidified, but the outside is not. But then you quickly dip this sort of coaxial flow happening along with this polymer film and whatever the internal core, etc., is there quickly into the solution bath. So that will solidify the exterior surface or the outside surface of this fibers, right? So the fibers, as it, I mean, the liquid as it turns to come out from this nozzle, the inside is already, inside to some extent will already be solidified because of the liquid jet in the hollow side. So it will not try to collapse, right? The whatever this spinning, this is called wet spinning technique. So when the fibers are actually, I mean, the liquid is actually coming out from the nozzle or from the needle, it will, the inside will not collapse because there is already a liquid jet running inside, right? And the outside will still be fluid like, or it will be rich in the polymer, but immediately as it puts into the gelation bath, the outside will also be solidified. And then you try to have this spooling arrangement so that adequate residence time is maintained. And then you try to wound it up. So now there is a continuous flow of the polymeric liquid as well as this water in this coaxial syringe arrangement, right? And a lot of factors affect the membrane pore formation apart from the polymer chemistry or the polymer composition. It's about the temperature of the gelation bath, the flow rate, the relative flow rate or the velocity of the polymeric solution with respect to the the water jet. So if their velocities are different, then there will be also some shearing action on the interior surface, right? So a lot of these factors play a role. Temperature also is another issue. Presence of additional salts in the water, right, could also be an issue. So all of these factors play a role. There is one more way to prepare a membrane that is typically known as the track etching process. So what is this track etching process? This is slightly more sophisticated process, but the advantage is that you can create a very uniform, pore distribution. So in all these types of the polymeric phase inversion, it is actually when this when this demixing of the polymer and the antisolvent, that is water, takes place, there is diffusion in the polymeric layer, and that's what create these pores, right? And these pores are of very non-uniform nature. Even though there is some mean pore size is there, do exist, but the shape and the structure of these pores is very non-uniform, right? Because of this diffusion, Brownian movements of the polymer due to this thermodynamic process. But what is this track etching process? So in the track etching process, you try to mark or label the points on a polymer flame based on a radiation source. So what do I mean by marking or labeling? Is that when you apply the radiation source, most likely it is the UV radiation, at certain points, right? I mean, these UV lights are not like uniform illumination. It's how do I put it? It's placed. I mean, it's like point sources. It's like laser pointed sources, right? So it's like laser pointed sources. You are applying that at specific points in your polymer film, right? And what does this laser, I mean, point sources do is that wherever it is illuminated at the particular point, and you can have a small, this width of the lasers illumination also. It could be, I mean, it could be like only few microns or even less than few microns. That is possible to do at that much precision, right? So that kind of, what is called this etching. So what does this radiation source do is that it etch the surface. What do I mean? So I mean by etch is that at those particular locations, because of the action of UVs, the chemicals or these, this polymeric molecules get to some extent modified, or they get to some extent activated, right? They some, or to some extent due to some UV irradiation, they react and their chemical nature changes, but only limited to that particular source region, right? Wherever this radiation is getting illuminated. Now, when those points are like sort of marked, Marked means what? Because of this, UV laser type of radiation, those particular points are actually labeled, or their chemical nature is slightly modified. And now when it is put into the etching bath, so etching bath contains some chemicals which acts only on the UV modified polymeric molecules. Okay, so only those points it will act, rest will remain unaffected, right? And that it will act and it will dissolve that part of the polymer, but others will remain unaffected. This is how the action happens. So once you have this laser, acting on this surface, generally these films are, too thin. So on the laser acting, it will create, so this dotted line essentially tells you that this layer of the molecules get exposed to the radiation, to UV radiation or some other X-ray radiation, whatever this is, and they got partially modified. And now in this etching solution, as it contains some other chemicals, it acts on this, this modified chemical, these molecules only, and then slowly it reacts and dissolves away those molecules. And finally, you get, like a small hollow, what should I call, pore in that part. So this is like very well formed pores. So there is no irregularity. The pore size is also very uniform, and you get a very sharp cutoff of the membrane. I will tell you what do I mean by the cutoff of the membrane. So I hope all of you got an idea of this. What do we mean by this track etching process? So it is like you are stamping something, and then you are trying to dissolve only those labeled portions. Of course, it has some limitations. First one goes by that is very expensive process. Second one is that there is a practical limit up to which you can have the pore size. So that is generally, not less than 100 micron, or 100 nanometers. Below that, it is not possible to achieve. I mean, that much, point width of the laser source is still not very well developed, right? So generally up to 100 micron, this is good. And also the, the pore density is also an issue. So there is a limitation to that also, right? So this technique is very similar, if anyone of you is aware of, is known as photolithography. Right. So photolithography is a very popular and a sophisticated technique for preparing these sort of semiconductors actually. So it is actually inspired from there. It's very similar to photolithography. But anyway, this is acting on a polymeric film, whereas photolithography acts on completely different sets of polymers. Okay, so now this is how a track etched membrane is prepared. So before we talk, so let me also talk about the modules. So this is one module. This is generally known as the plate and the frame module, and it consists of the flat sheet membranes. So what essentially is done, you have these packings of the flat sheets placed between, two frames. Right? So if you try to look into these arrangements, you can see here that there are these. There are these, in the center you have these spacer regions, and across the spacer regions you place these membranes. Or you can think in another way, that between two spacers you also have two membranes, and there is also a flow channel across. I mean, there is one feed channel in between these two membranes, and through the spacers you can take out the filtrate. So the spacers are also porous, and these are just support materials. So this is like alternate frames you can put together, and you can really have a large membrane or a filtration surface area within a compact volume, right? Because you can have these compartments either stacked vertically or stacked one over the other, right? And all the permeate lines or the filtrate lines can be joined together, and you can have a cumulative volume. Similarly, the feed channels can be in parallel modes. Right. So this is one type of module. This is generally known as the plate and the frame filter module. This is generally good for microfiltration membranes, or where the permeability is really high, because there is a lot of pressure drop in this arrangement. Right. So there is a lot of pressure is actually lost from the feed side actually going into the module. Right, so generally higher pressures will lead to higher, I mean, if you have higher pressures, then a lot of pressure will be lost due to this high pressure drops in this module arrangement. So generally that is not preferred, and that's the reason why microfiltration, which operates under lower pressure, is preferred. This is another one, and this is the most popular one in the industrial scale. This is generally known as the spiral wound membrane modules. So it's again a flat sheet membranes, but these flat sheet membranes are actually rolled or wrapped up across a tube. And this arrangement, I mean, analogous arrangement is like if you ever tried to stitch your clothes, you will see that they will have these metered rolls of cloth, right? And how much you need, they will just take out and they will cut it. So just think of how those rolls are wounded up. It's also the tissue paper roll you can think of. So it's a very similar way. These membranes are rolled up, but with additional, channel spaces or spaces between the each roll or each winding. Why? So that when the liquid tried to, pass through this membrane or through this layers, there will be provision for the permeate to also be collected, right? So there is so you can see there is a region where you can pass the feed solution. So the feed solution passes actually in the interstitial areas between the two layers, and the permeate is collected in the central hollow tube at the end. So all the filters, all the liquids that is filtering through each of these membrane windings are again collected, and it goes back to the arrangement is such that it goes inside to the central core where the permeates are collected, because there are some hollow points here. So that will collect all the filtrate that is produced by these membranes, and the feed is actually fed on this surface area. Just have a look. I think the schematic is very nicely showing here. So that is how you try to inject or introduce the feed into the system, right? And there are gaps. There are spacer materials as well as some supports to these membranes, which creates these gaps, and they also acts as the permeate collection materials, right? So that is how this this spiral wound module actually works, and they are quite industrially favored because you can really have a large surface area within a small volume space. Just try to feel the compactness of this module, right? So this is the reason why they are quite nicely favored. From the perspective of pressure drop also, since the flow, there is no restriction or hindrance to the feed side flow, the pressure drop is also minimal in this case. So they can also be used for higher pressure systems. So all the reverse osmosis and these filters are generally prepared in the spiral wound configuration. Next, talking about the hollow fiber module. The hollow fiber module is like analogous to the shell and tube exchanger. So you can think your tubes as the hollow fibers, the shell as the outer casing. The only difference, the tubes here in this case have hollow walls or surface areas, where in the shell and tube exchanger there is no mixing of the fluids, right? So just try to look into this arrangement, this picture. So the feed is injected into all of these hollow tubes, right? And the intermediate spaces between, so how these hollow fibers are packed is that they are fixed to the casing, and all the interstitial spaces at the entrance side are blocked, right? In between two fibers, whatever. Otherwise there will be mixing of the liquids, right? This because once the liquid, I mean the contaminant of the feed liquid goes into the hollow fibers, it will produce the permeate and it will come out through the porous walls and collected in this shell side, right? So if now you already have some fluid in the shell side because of some leakage between the gaps, then there will be mixing of the permeate, right? And that is not allowed. Okay, so that is the reason why these regions between the hollow fibers, but not their mouth or the hollow cores, is actually blocked with some resin or some glue, and that is fixed to the end of the casing in both sides. and these configurations are not of 2-1 or 2-4, those kind of configurations, all 1-1 only, right? So there is no shell side flow. Okay, there is no shell side flow. The shell liquid is the filtrate that is produced from these hollow fibers. They are collected and then they goes out through the tapping points on the shell side. There is no shell side flow. Externally, there is no shell side flow. It is the liquid which is acting as the feed goes through the hollow fibers, and through the fiber walls it comes out as a filtration mechanism, and then it is collected, all of them together in the shell side, and they are collected in the permeate. So this is how the hollow fibers or the hollow fiber module is prepared. Now, of course, each of these modules have their own advantage and disadvantages, and we have discussed most of them. There are some more types of the flat sheet. Maybe I should have told them right here only. Let me try to do it. So for the flat sheet configuration, there are some more types. One is known as cross flow. Another is known as the batch cell. So this is a continuous type, and this is a batch type unit. How does this look like? So you just think of a single layer in the plate and frame filter paste. Something like this. So you have two plates, right? And in between those two plates, you fix your membrane, right? So membrane is on support at the bottom layer, and you try to pass the liquid over this membrane surface in between the gaps of these two plates, right? Right. So now since the flow or the flow of the liquid over the membrane surface is tangential to the surface, right? But since the pressure in the inside or the surface of the membrane is higher compared to the outside, there will be permeation. So there is a kind of cross flow action over the membrane surface, right? So if you have this as your membrane, so the liquid is flowing tangentially over the surface. But since the pressure on the feed side is higher than the pressure on the permeate side, there will be permeation through this porous membrane or this porous sheet, right? So this, all of these porous sheets will be collected through one port, and that will act as a filtrate. The batch arrangement is very similar to a simple, filtration type, very much like how you separate using a filter paper. So let us say you have a big cylindrical vessel, and at the bottom you place your membrane, and over this your feed liquid is there, and you try to pressurize this feed liquid, right? So this is the pressure on the over the surface of the membrane is higher, there will be permeation. This is what the batch type. Right, so this is how typically a batch type unit looks like. There is a lot of several internal arrangements so that there is no leakage, and you can nicely apply the pressure over the membrane surface. All of these can be done. Right, so these are generally the batch type, and this is generally the cross flow type. But again, in the cross flow type, there are several variations. So let us not digress too much. Let us stick to the point. So what are some differences in the flow arrangements, right? You can also have a kind of this cross flow filtration where the flow rate is directly over the membrane surface. That kind is also possible. It could be also, you can have this sort of batch filtration in a hollow fiber system also, right? So how do we have hollow fiber system? How do we have a batch mode of the filtration? Is that if you think of this module, and as the feed goes in, you do not allow the feed to come out on the other side of the liquid. You block that other side, so all of the feed has to come out as the permeate, right? So what do we call it as a batch, and when do we call it as a cross flow or a continuous flow? Is that there is continuous inlet and outlet of the feed fluid. That is what we call as a cross flow or a continuous flow. right? If there is no outlet of the feed side fluid, then we call it as a batch filtration or a dead end filtration, because the flow rate or the flow of the molecules on the liquid feed side do not come out, right? They come out only as a permeate. That is also possible. So you can have this batch mode of the filtration even in not in the this kind of sheet type filters. You can also have it in the hollow fiber type of filters also. Similarly, cross flow is also possible, as I have shown in the flat sheet kind of things. Generally, the hollow fiber arrangements are also of cross flow or continuous nature, because the fluid flows through the fibers and it also comes out on the other side, and in between there is permeation, right? So just trying to give you a glimpse of the different batch and the continuous types and in different types of module configurations. Now there are some particular arrangements, particular advantage if the flow over the membrane surface is tangential or perpendicular to the surface. So the particular advantage over why this cross flow idea is evolved is because if there is continuous flow or this flow of the liquid tangential to the membrane surface, so any solutes that is deposited, particularly the solutes which is removed or retained by the membrane and not allowed to pass through, they will get deposited on the membrane surface. So they can be removed by the cross shearing action by the liquid. That is one of the particular benefits of this cross flow type. But in the vertical type or the where the flow is perpendicular to these membranes, this action is not present, isn't it? So that the deposition layer will continue to grow, but in the cross flow types, their growth will be arrested or prevented. Okay, so we stop here today. We'll continue again from here, and we'll look into the more into the mathematics based on the film theory of these systems. Okay, so any question, guys, up to this? Anyone? Have any question? If not, then we call it a day. Thank you. Thank you, everyone.
Thank you, sir.